Good afternoon. My name is Tiffany Meeks. I've been in the Navy for 7.5 years. I spent 2 years in nuclear engineering school, 4.5 years working with nuclear reactors, and the last year talking to students like yourself. I think my favorite part so far has been helping the public understand nuclear energy and how beneficial it can be. Before I begin, I want to say thank you for the outstanding questions you've come up with. I especially enjoyed looking at the different types of reactors and comparing them. I don't know enough about the design of most of them, but from what I learned, I believe the pressurized water reactor is better than boiling water reactors like those in Fukushima and RBMK reactors like those in Chernobyl. Nuclear energy is the process of taking heat generated from fission and turning it into energy that can be used for electricity and propulsion. Nuclear reactors are used all around the world and are more common than you would think. The US generates the most electricity in the world using nuclear power, but it still only makes up 20% of what we use nationwide. If we were to remove nuclear energy from the US today, it would mostly affect large cities in the eastern half of the US. There are some places in the US where nuclear energy isn't used. Most reactors are found in densely populated areas. In areas with low population, we use other forms of green energy, like wind and solar. To this day, nuclear energy remains the highest production and carbon-free energy. Nuclear energy is all about fission. Fission is the breaking apart of atoms to create heat. Some reactors use plutonium, but uranium is still most widely used. As the neutron strikes an atom, it causes it to become unstable and break down. As the uranium breaks, it produces two isotopes and several neutrons. Those neutrons then go on to collide with other uranium atoms to create more reactions. This results in an exponential rise in heat. We control the reactions using control rods. In most reactors, we use hafnium because it can absorb the neutrons without undergoing fission. If the control rods are completely inserted, the reactor is considered shut down. Small amounts of fission still occur, but it's not enough to produce significant amounts of heat. As control rods are raised, more usable uranium is exposed, allowing for more reactions to occur. Chernobyl's control rods had graphite tips, which caused more reactions to occur at a lower level. There's a lot of science behind it that made it useful, but in combination with other problems, there was a major malfunction. The world learned from that mistake, and we've come up with better designs. Pressurized water reactors, as you see here, are most common in the Navy. We use the steam generated to spin turbines and produce electricity and propulsion. Commercial reactors are also pressurized water reactors. What this means is that there are two closed systems and an open system. The first system contains the water that meets the uranium directly to pick up heat. The heat's transferred through piping to the second system before returning to the reactor to repeat the cycle. The second system takes the heat and boils water to produce steam. The steam transfers to the turbines before moving on to the condenser to be returned to water, repeating its cycle. The open system is the cooling water for the condenser and is typically ocean, sea, or river. The likelihood for radioactive water to reach open water is reduced having the second system. In boiling water reactors, there's only one closed system. You can get more energy from a gram of uranium than you can find in a ton of coal or 3 barrels of natural oil. Since uranium can be compressed into relatively small size and arranged for use over time, they don't have to be resupplied as often as coal and gas plants. Commercially, reactors are refueled every year, where coal plants require daily refueling. You can get twice as much electricity from a reactor in 1 month as compared to a coal plant in 1 year. For a general idea, 1 gram of uranium can power a light bulb for 26 years. 90% of the spent fuel material in a nuclear reactor can be recycled into new batches of fuel. The other 10% is then buried in secured holding areas. Our current national storage capacity will last us about 5,000 years. Safety is the biggest concern with nuclear power. Preventing the release of radiation to the public is the main goal. Our reactors and their piping systems are surrounded by layers of lead, water tanks, and concrete to prevent the release of radiation. We have equipment located in each system that monitors the radiation. If abnormal levels are found, the reactor is shut down until the problem can be resolved. With all of the shielding methods in place, the amount of radiation you get living next to a power plant for 1 year is about the same as eating a banana. Nuclear engineers are always training in scenarios of malfunction and what actions are required to prevent damage to a reactor and the release to the public. We learn how each system works together to keep the reactor safe. Another way of promoting safety is controlled maintenance practices. These procedures are in place to prevent failure of key components. If you don't follow procedures properly, it can result in irreversible damage. 3 Mile Island is a great example. There were major issues during a modification of a procedure that resulted in the damage to a safety valve. Inappropriate action by the engineers led to a casualty. As protection from natural disaster, most reactors in areas with earthquakes have built-in detectors to force a safety shutdown. The backup cooling systems will keep the reactor safe. If the cooling system becomes unavailable in the same or subsequent accidents, it can result in disasters like those at Fukushima. The use of nuclear energy is still a largely debated issue. I'd like to see more plants used, but unfortunately we do not have the manpower to sustain. If we can educate more on nuclear power and garner more interest in engineering, I'm sure it would be used a lot more. Some of you asked what I'd like to see technologically and how it would benefit society. I would love to see nuclear reactors used in smaller applications. To be able to power mass transit would be phenomenal in lowering our carbon footprint. But it's not a feasible idea to put small reactors in vehicles and planes, as the potential for disastrous accidents is too high. Nuclear engineering is a great career path for those interested in math and science. Most of the principles used in engineering are physics, chemistry, algebra, and thermodynamics. Since engineers are required to know a lot educationally, we're also paid very well. Yearly salary for engineers in this field will start at about $80,000. I'm so thankful of the time you've taken to learn about this field of science. There's so much more to learn. Thank you for all of your attention and providing me with fantastic questions. I hope I answered them all.